So section 5.3, we're going to talk about perpendicular bisectors, the point where they all meet, and some special properties about that, and angle bisectors and the point where they meet, and some special properties of that. Before we get there, we're going to talk about what it means to be concurrent. If we are talking about two lines that meet, what do we call that? Intersecting. So if we have two lines that meet, we call it an intersection or intersecting. Okay. But as soon as we have three lines or more, that is actually called concurrency or concurrent. Those lines would be concurrent because they all intersect in one point. So when you have three or more lines that intersect at one point, they are called concurrent. So if three or more lines or line segments or rays, okay, intersect at one point, then they are what is called concurrent. In my little drawing here, four lines intersecting at a single point, and that point has a special name. That name of that point is what we call the point of concurrency. Okay, so when we have two lines that meet, we call it an intersection, and we would have the point of intersection. When we have three or more lines, we use the word concurrent, but it just basically means intersect. The concurrency of perpendicular bisectors theorem says the perpendicular bisectors of the sides of a triangle are concurrent at a point, which we looked at yesterday. They all meet in one point. One of the special things about that point, where they all meet, is that that point is going to be equidistant from the vertices. What does equidistant mean? Same distance, right? Equal distance. So if we drew in or had the perpendicular bisectors of each side of that triangle, which I sketched in blue, I don't know if they're exact, I just sketched them. They all intersect at point P, which means that if we go from point P to each of the vertices, those distances will all be the same. Okay. The name of that point of concurrency of the three perpendicular bisectors is called the circumcenter of a triangle. And what it is that point of concurrency of the three perpendicular bisectors of the triangle. Because point P is equidistant from each of the vertices, we can draw a circle with the center at point P, and it's not going to work because my drawing is a sketch. Let's steal this drawing so I can show you. So if we have a well-constructed triangle and not a sketch, we can draw a circle with the center at point P that will touch each vertex. Okay. So this circumcenter, point P, is the center of a circle that will touch each vertex of the triangle. What that's called this circle is what is called circumscribed about the triangle. Okay. So one of these special points that we're looking at is going to be the circumcenter, and we can draw a circle that will touch each vertex, which is a circle that is circumscribed. Circumcenter, circumscribed. They go together, right? Another point that we're going to look at is one where we can draw a circle inside the triangle and touch each of the sides, which is going to be inscribed because it's inside. So circumscribed is outside, inscribed is inside. So we're looking for the circumcenter of a triangle. What are the coordinates of the circumcenter of the triangle with point P, with vertices at point P06, Q00, S40? So Q is at 00, P is at 06, and S is at 40. Just kind of a little sketch. And the reason it'll work for us is because it's nice even numbers and a nice right triangle. If this was not a right triangle, this would be a lot more difficult. But what is the circumcenter? The circumcenter is the point where the what meet? The three perpendicular bisectors. Okay. Now, I told you this is a right triangle, which makes this a lot easier. And we have a nice horizontal line here and a nice vertical line here. What's going to be perpendicular to a horizontal line? Vertical line. And what's going to be halfway between 0 and 4? 2. And what's going to be perpendicular to this vertical line? A horizontal line. And what's halfway between 0 and 6? 3. So at 3, we'll go right about here. So these two lines, this is the line, a vertical line of x equals 2, and this is a horizontal line of y equals 3. So this point right here is the point. So we put x first or y first? Always x, so it will be 2, 3. So the answer to our problem, what are the coordinates of the circumcenter? 2, 3. So because we have a nice right triangle with horizontal and vertical lines, we basically just have to figure out what's the middle of 0 and 4 and what's the middle of 0 and 6. If this triangle was crooked or not a right triangle and it wasn't nearly as nicely set up, this would be a lot more difficult. But for now, we're sticking with kind of the basics. The second theorem is the concurrency of the angle bisectors theorem. So as we saw yesterday, if we take the three bisectors of the angles, they meet in a single point. The special thing about that point is that it is equidistant, so same distance, to the sides of the triangle. And remember, when we do the distance from a point to a line, we always do it on the perpendicular. So these three little blue segments are all equal to each other. Inside the triangle, that instead of touching each vertex, touches each side. This circle is what is called inscribed. So in center allows us to draw an inscribed circle. Inscribed in the triangle. So inscribed is inside, circumscribed is outside. So we have the circumcenter that allows us to create the circle outside, which is circumscribed about the triangle. We have the in-center, which from that point we can get a circle that is inscribed in the triangle.